This is that last slide on 5.1 that had notes section, and you'll notice your paper looks like that, and then there's a space for you to sketch this, if you would sketch it. The purpose of this slide is to say, sometimes you have equations that are not necessarily one-to-one. For instance, a quadratic is not one-to-one. So, meaning, if you recall from yesterday, hold on. All right, there we go. It fails the vertical line test, or horizontal line test, which means that if I take it and graph its inverse, it would fail the vertical line test. And the inverse would be this right here. Now, don't draw this whole curve, but it's important for you to see this, to know that that purple curve is the inverse of this quadratic. You can see clearly the purple curve fails the vertical line test, but the beauty of it is, and I say beauty loosely, you may have a different term for it, is we can come over here and say, okay, I really want it to pass the vertical line test, so why don't we just cut off part of the value, and then bam, now it passes the vertical line test. To cut off part of the curve, you are restricting the domain. You're saying don't plug every number in, only plug in numbers that will allow me to graph half the curve so that it passes the vertical line test. That's the tweak that you can do here. So what does it actually look like for, like this right here? This is a quadratic that has been shifted down to. That's the mother function that's been shifted down to. If you look at the inverse, look right here. If you want to write this equation down, this function, it says f inverse of x equals the square root of x plus 2. Can you remember from chapter R and I think chapter 1, how do I find out what x values are allowed to go under a square root?
Make it equal 0.
So you take the radicand and not set it equal to 0, but it can stay greater than or equal to 0. Because it can be positive or it can be 0, it just cannot be negative. So the radicand is x plus 2. Solve for x. So this inverse function would satisfy the function requirement, the vertical line test, if, I knew that was going to happen, if the domain stays greater than or equal to -2. So we've restricted the domain. We're saying don't plug any number you want in. Only plug in numbers that are at -2 or counting up. And I don't think that's in the homework necessarily. I'll look. But I wanted to give that slide its due diligence because I wanted you to see that quadratics are not off limits if you restrict the domain. And then I do have, this is 14, right? This is number 14.
What the heck?
It's asking for you to explain your process for verifying that this function and this function are inverses. This would be that composition that we did yesterday. You have to do it both directions. If you look at the formatting, for instance, if you're checking this one first, then you would be doing f inverse of the function f, and then they're asking how does that look when plugged in, and then how does it look when cleaned up. This is when I don't like my math lab, but I have no way around it because GNTC wants us to use my math lab. So be able to do it for the one homework problem, but then just understand the math behind it, okay? The steps behind it. And that would be what we did on the slide yesterday, where we actually did it. How did you feel with the slide yesterday?
It was much easier.
It's a lot easier. I find this challenging. I find this where you kind of lose the math, in my opinion, but that's beyond my control. So I thought I would give this to you as a help for understanding the My Math Lab way of asking it. Are there any questions on 5.1? Okay. 5.2 is properties of exponents and exponential growth and decay. So I'm ready to go to 5.2. I'm going to put all of the Chapter 5 homeworks due by the test day. Okay? So that way because, for example, stuff like that, if you're struggling with that, but you actually understand the math, I don't want you to feel punished by getting a 90 because you needed to ask me for help on that. Does that make sense? So please don't take that as an opportunity to wait till the exam to do the homeworks. Please don't do that. I don't think I marked Dakota absent yesterday, and he's out. All right, so let's move on to 5.2.
What are you doing?
I
would like so. Wait.
That's better.
Is that my fault?
No.
Then you need it for me. Quads are hurting. All right,
Right.
5.2, exponential functions and graphs. This calls on your properties of exponents and exponential growth and decay. So a lot of stuff that you learned in Algebra 2 should come back to you, okay? And if not, I have dedicated the first slide to, hey, remember this from Algebra 2? You're welcome, instead of diving right in. Most college professors do not review. You're welcome. I choose to review so that we can mitigate stress and chaos when I throw the new stuff at you.
Thanks for helping.
You're welcome. So if you go to this slide right here, let's refresh you on how to do this. Yes, you could just type it in your calculator. I need you to know the mechanics behind it, not just can you type it in your calculator.
Answers always good.
What do these exponents mean? That's the goal here. So for instance, 2 raised to the 3rd power means,
2 times 2.
thank you, it means 2 times itself 3 times, correct? Which is what? 8. Now in expanded form, this would be 2 times 2 times 2. I'm not necessarily saying you're going to be writing in expanded form every time, but I need you to remember that is the mechanics behind 2 cubed. Y'all with me? 9 squared, what does it mean?
9 times 9.
9 times 9, which is 81, which is called a perfect square, and the square root of it is 9. This is called a, 8 is called a perfect cube, and the cube root of it is 2. We're getting back to radicals, so it's important that there's a reason I'm asking these questions. Okay, 64 raised to the 1/3 power. First of all, I cannot stand when it's written like that. I like to write it in a vertical orientation because then I can actually see this is in the top, this is in the bottom. It is definitely up in the exponents place. I want you to evaluate this by hand, by rewriting it in radical form. Do you remember how to do that?
No.
The root goes in the ground.
Roots grow in the bottom, in the ground. What is the root in the fraction? The 3. That is the root, and then the top number is the exponent. Remember that?
No.
Let's make a note. There's a reason why we're doing this. I'm going to draw an arrow. I'm pointing to the 3. That is the root. And now I'm pointing to the 1. That is the exponent. I actually like writing with this better than Penny. Penny lags.
I hid Penny in a high place. Her pen.
What are you writing with now? A highlighter.
Kit Kat. Did you buy that off of Colby Brew?
Okay. What is
Oh,
the
if it's
cube
so
root
high.
of 64? Meaning, what number multiplied by itself 3 times would give me 64?
4.
4.
I just scanned my paper.
Now, 9 to the 1/2 power. I want you to try that. Rewrite it in radical form and then evaluate it.
It's one before.
Whoa.
Close.
I got real low.
Oh, amigos?
I tried to do it.
Did you say amigos? I thought you said amigos.
Mi amigos
First
es
I said
muy
then I was
bueno.
like,
Quarterback.
I did.
Yeah, I'm just
I did.
I'm
He finally got some playtime.
Puta.
What'd you get?
3.
So this is, what is the radical form of this?
Square root of 9.
This is the square root of
Open up.
9. And if you're wondering where the 1 and the 2 went, this is an understood square root. We never write the 2. And this is 9 to the 1st power, which is irrelevant. So it's 3. Right? This is important. This is where, this is going to help. All right, 8 to the 5/3. Tell me in radical form.
Cube root of 8 to the 5th.
Cube root of 8 to the 5th. Now, there's 2 ways to do this. You could go to your calculator and just type it in, or you could try to remember how to break this down. If you're taking the root of a base to a power, and the power is higher than the root, then you can pull out one of the bases as a perfect root. So what do I mean by that? This means there's 5 8s here, correct?
Yes.
And this means take the cube root of them, which means pull I say pair. I don't mean pair as in 2, I mean pair as in pairing. Pull out a pairing of 3, because that will simplify as just 8, correct?
Yes.
Okay, I'm going to break this down. So this is the cube root of 8, 8, 8, 8, and 8. Pull out a pairing of 3. The cube root of 8 to the 3rd would be just 8. Right? Go with me? Okay, which would leave, how many under there?
2.
2. All right, so I'm going to write cube root 8 times 8 is 64. What is the cube root of 64? 4. So this ends up being 8 times 4, which is
32.
32. We are not going to be breaking these down by hand. I just need you to do it a few times so that when I teach you the other stuff, this is the foundational understanding, and then the other stuff will make more sense, okay? Yes. So this is 8 to the 5th power, which means there's 5 of them. Because it's a cube root, if you pairing together, couple. No, that's worse. That sounds like 2. Group. There you go. Pull a group of 3 out, because it's a cube root. The cube root of 8 cubed would be just 8, because it cancels. Cube root of 8 cubed. Those cancel. You see that? So I pulled that 8 out right there. Now what's left? There's 2 left. That's where the 64 came from. And what is the cube root of 64? 4. So that's how we calculate it by hand. 25 to the 3/2 would mean what? Square root of 25 cubed. 25 cubed is what? I don't know off the top of my head.
15625.
15625. Now see if you can take the square root of that.
It's 125.
There you go. So this one ends up being nice. I would not expect you to do this one in your head. If you type this in the calculator, you're going to get 125. If you need to see how to type it in, stand by. Marty, will you open the filing cabinet drawer up to the window and the wall? There you go. Thank you. All right. Yeah. Square root 25 cubed. All right, here we go. So square root 25. Hit the caret button. Cubed. There you go. All right. 5 to the negative 1. There's not really evaluating this. There's just rewriting it to get rid of the negative 1 in the exponent. That does not mean inverse here. We're not talking about functions. We're talking about the number 5. What is it? You know? What is it?
Negative
Yeah.
5.
So this negative 1 means take the base and the power and move it to the opposite position, right? When I say opposite position, I'm just going to move. I know I'm blocking it. It's over 1. So I'm going to take 5 to the 1 power, and I'm going to bring it to the bottom, which leaves nothing on top, which means there's an understood 1, and 5 to the 1 power is just 5. So it's 1/5.
1/5.
So what would 7 to the negative thirds be?
343.
Correct, and the 343 came from?
1 over 7 to the third power.
Very good. So this would be 1 over 7 cubed, which cleaned up looks like that. What is anything to the 0 power?
1.
Careful. I want you to think of it this way. This is the way I remember it. Write the base 0 times. Which means don't write it at all. Well, in math you can't just say, okay, I'm done. Like there's something there. What's understood to be there? There's a 1. So that's how I remember the difference between anything to the 0 and anything to the 1 power. It's literally telling you write the base 0 times. Of course, you could type it in your calculator and you'll also see that it's 1. Doesn't matter how ugly it is. It is 1. Okay? All right, so that was a crash course reminder of properties of exponents. Now we're getting into the stuff that you should have learned in Algebra 2, and then we just dive deeper with it. Graph the exponential function. Am I good with this so I can change this?
Yes, ma'am.
Graph the exponential function f of x equals 2 to the x power. We know it's exponential because where is the x? It is in the exponent, hence the name. It's exponential because the x is in the exponent's place. And if you go and look at the graph, the curve is increasing or decreasing exponentially, depending on what type of function we have. Now, if I wanted you to just graph this in the calculator, you would type it in y equals, you would type 2 caret x in y equals, and then if I wanted you to copy the graph to your paper, what do we need to know from the graph?
Table.
The table. So you can do, if you need to, I'm going to put a question mark in front of it because this is optional if you wanted to check it. If you need to, you can check table set The way you get to that is second table. It's second window. That's the way you get to it. I'm going to put in parentheses. It's second window. And it will pull up the table set feature. Table set is asking, how do you want the giant table to start, counting that, and then count by? And do you want it to just automatically generate the numbers, or do you want to ask the calculator to generate the numbers? So if we look at it, I'm going to go to y equals, and I'm going to put this in here. And then now I'm going to table set. So second window. Mine's saying it's going to start at 0. I don't want it to count by halves. That's from that last problem we did. I want mine to count by 1. And I leave it on auto because I just want to see the whole running table. Hit enter, and then now to get to the table, hit second graph. You'll notice above graph, it says table. There's your giant T-chart. And now pick the numbers that you can nicely fit on the coordinate plane that I've given you. To get to some of the negative ones, you arrow up. And you can see as I arrow up, those numbers are really ugly. So I probably wouldn't graph those. I would graph the nice ones, and then I would give an idea of where the curve is. So I'm going to graph -2 and then 0.25, meaning it's just a quarter. Then I'm going to graph -1.5, 0, 1, 2, 1, 2, 2, 4, 3, 8, and you can see where the curve is. So you should get an idea that the curve is like that. This will be second table. To see the table, you would do second, what do we say, graph? And then you would copy the values. All right, go to the next slide. This time you're graphing f of x equals 1/2 to the x power. Are y'all good with this slide? Mm-hmm. Before you graph it, you can go ahead and type it in y equals, but I would like you to make a note. Be careful. What I mean by be careful, in the calculator, all right, it is not 1 divide 2 caret x. Do not type 1 divide 2 caret x, because if you do that, I'm going to draw an arrow to say, like, if you type that, that is actually 1 over 2 to the x power. It will only raise the 2 to the x power. It will not raise the entire 1/2 to the x power. So there's a big difference. You've got to put parentheses around the 1/2 to say, hey, take the 1/2, raise the whole dang thing to x, not just what the caret's attached to at the end. So in the calculator, you will use parentheses. So here is the correct way to type it in. It'd be parentheses, 1 divide 2, close parentheses, caret x. And that will correctly enter 1/2 to the x power. And then you can go to your second table and copy some pretty numbers. I don't have the table on my paper, so I'm going to do the best I can with where I think my points are. Now, you're going to notice that in the middle of the paper, there's this giant, like, before we plot the points and draw the graph, please note, and then you can see this thought process here. Y is actually f of x. In this case, it's 1/2 to the x. What's another way to write 1/2? You could write it as 2 to the negative 1 power. What's another way to write that? Well, that would be negative 1 times x, so you end up with this 2 to the negative x power. That is the same graph. That's the same graph. You don't have to go that way, but that's the same graph. That's the relationship between the two. Now, look at the graph at the top, look at the graph at the bottom, on your paper, on your notes.
It's the inverse.
They're totally different. This one is, looking for a buzzword.
Puzzle. No.
Any buzzword?
No. I think I heard it started with an I.
Increasing?
It is increasing. There's a word to describe this type of exponential problem. If it's increasing, it starts with a G.
Growth.
It is growth.
Oh, it is.
This is an exponential growth problem. This is an exponential decay problem. There seems to be some confusion about this among some well-known people. I won't go there. Anyways, look at the difference between the two graphs. Reading it from left to right, yes, we can determine if it's increasing or decreasing. But can I determine if it's exponential growth or decay from the graph? Not necessarily. I need to look at the actual function. Look at the equation between this one, might be easier to look at your paper, and this one. What is the difference in the equations?
Decay is less than 1.
There you go. What did you notice about the other one? It was greater than 1. Okay, so that brings us to this slide right here. Now these are totally different graphs. These are just a bunch of examples, all put together on one graph over here and one graph over there. If you just look at the graphs, you don't know a lot about it because I can take an exponential decay, flip it over the x-axis, and if you're just looking at the graph, you're going to call it a growth. So you have to be careful. You cannot look at the graphs. You've got to look at the functions. Notice this is 4 to the x, 2.5 to the x, 1.8 to the x. Notice over here, 0.7 to the x, 0.4 to the x, 1/4 to the x. So the difference is, get artsy-fartsy with this, meaning take good notes on it. I'm going to throw this away because no one, where's my trash can?
Okay.
Alright, anyways, just,
You just click on it, really.
won't let me. Oh, shoot. Alright, let's get, pretty with this. Alright, watch out. Check the base.
Well, we need space underneath it.
Yeah, we're going to do something down here. Yeah. Check the base of the exponent to determine, spell it right, to determine which type. Check the base. Don't go by the picture of the graph. If the base is greater than 1 It is growth. And when we say greater than 1, I do want you to make a note, like, I don't know where you want to make the note, so just, let's say, don't focus on decimals. Some people, when I say greater than 1, they like to think, okay, big numbers. And if I throw 1.8 at them, they just see a decimal and they might run with it and think, oh, that's a fraction less than 1. No, the whole part's a 1, and then the fraction's the 0.8. So don't focus on decimals, focus on just, is the number bigger than 1 or less than 1? If I was trying to graph it, where would it fall? Over here, if the base is less than 1, it is decay. And remember, like I said, I can take an exponential decay, which means it's running like this, and I can flip it over the x-axis, which means now it's running like that. And if I was to just read the graph, it looks like it's increasing. But really, all I did was put a negative in the function to reflect it. So be careful. Now, what we're going to do is this right here with transformations of the graphs. We're getting back to recognizing the mother function and then shifting it right, left, reflecting it up, or reflecting it over the x-axis. Yes, yes. And it all stems from the mother functions, okay? The mother functions, and when I say mother function, there's not like an actual true, oh, it's x squared. That's the mother function of quadratic. I can't say the mother function is 1 to the x, because what happens if you take 1 and raise it to a power? What do you get? 1 every time, right? So nothing interesting happens. So 2 to the x is considered like the mother function, because if I do 1 to the x, nothing happens. Nothing grows. 2, things grow. And then 1/2, things decay. If I take 1 and raise it to the, if I do 1 over 1, that's still 1, nothing's going to happen. So exponential growth and decay functions are a little different when we talk about the mother function, because there's really no like baseline. It's just simplicity. Think 2 to the x or 1/2 to the x. All right, so go to this slide. Here is the mother function formula to keep in mind. So f of x equals, and b for base, like where that went, b for base, come on, put some space there because I'm going to put an a in the front, times, because sometimes there could be a negative in the front and it's going to reflect it. Then we have x minus h up here in the exponent's place, and then at the end we have plus k. Should look very familiar to vertex form of a quadratic. Numbers in each of those positions do different things. A would be if there is a number, like a multiplier in the front, it can be a -1, which means we're reflecting. Or it could be an actual number like -2 or +4 or another fraction, 1/2. But then you have the base of the exponent, which is where you actually know if it's growth or decay. Then you have up in the exponent's position, if there's a plus or minus a number, that's a right and left movement. Just taking the whole graph and then moving it right or left. If there's a plus or minus number on the end, that's an up and down movement. Take the whole graph and just go up or down with it. The only number that changes the stretch or shrink look of the curve would be A and, of course, B. What rate is it exponentially growing or decaying? That's B. And then A is, what else are you throwing in there to stretch it or shrink it? All right, so keeping that in mind, come right here. Look at this. 2 to the x. Grace was coloring yesterday. You can see, obviously. Nope. What is it? All right. 2 to the x is like the mother function, and then you have up in the exponent's place -2. So what's it doing? Shifting which direction? Right 2. Do you remember when we were dealing with quadratics? We said right here to watch out. I don't have room, but I drew an asterisk to say watch out for that number. It's always a sign change. If you see -3, it meant right 3. If you see +4, it meant left 4. So keep that in mind. So let's make note. First of all, is this growth or decay?
Growth.
It is growth because the base is greater than 1. And then it is shifting
Right 2.
right 2. So all of those points that you graphed on that 2 to the x power, we're just going to shift them right 2. So I think we had, if you plug 0 in, you get 1, so it's going to go right 2, right? And if you plugged 1 in, you got 2, so it's going to go right 2. Come on. If you plug 2 into the original, you got 8, it's going to go right 2. And you should be able to see the curve. Please don't sit there trying to graph 10 points. Just graph a few to get the general idea of where the curve is. Remember, the mother function curve was like right here. So you should be able to visualize, okay, it went right 2. All right, what about B? Is it growth or decay? It is growth because the base is 2, and it's going where?
Down 4.
It is simply taking the whole graph and it's dropping down 4. So my curve, normally I like to just put, it was usually about right there. So I'm going to come down to the 4 and I'm going to draw my curve like that. Now I think it shoots up a little faster than what I did. If you want to be accurate. If it bothers you to not be completely accurate, I think this ends up being here. Here. And then it bottoms out like right there. All right. The next one has a slight trick in it, and that would be what? They basically cup gamed it. It's not in the correct order that we like to look at it and read it. The base and the power need to be in the front. So if I do the cup game shuffle, this is a -0.5 to the x, and that is a +5 at the end. Now I can actually see it. Yes. Yes, it's going to be put down. So what type of function is this? What type of exponential? This is a decay, and it's because of that 0.5. and it has a negative in the front. The negative is what you are used to, like if an x squared had a negative in the front, it would go down, right? And y'all look again for dramatic.
Down.
So you've got the x squared. If it's positive, if it was negative, it would be reflected over the x-axis, and it would be opening down. Well, this is a decay, which means it's normally dropping like this, right? But it's going to reflect over the x. So this is a perfect example of why you don't judge the graph. You judge the function. I shouldn't say judge. Read. You don't read the graph. You read the function, because you cannot tell from an exponential growth or a decay by just looking at the graph. And then it's also going to go where? Up 5. It's going to shift up 5. So if you want some accurate points, if I can read mine.
There's not a sign change on the K, right?
Correct.
Okay.
Correct. That is what it is. The only one that has an issue is the one that's going to be right up in the exponent with the x.
Okay.
Alright, and then it starts like hook and laddering right there. You don't do that good. So see, if I look at that graph and I read it like a book from left to right, I would mistake it as an exponential growth. Because it's definitely increasing. An exponential decay can increase. And in this case, that's what you have here. As you read it from left to right, it's increasing. But when you actually look at the function behind it, that is a decay problem. The next slide, don't get happy here, don't exit out. I want you to skip the next slide, don't mark it out, just bypass it, and go to this slide. Oh, 2 slides. No, this slide, yeah. Go to this slide.
Bring it around and down.
So, y'all are very well versed on the number pi, right? Pi, 3.1415, yada, yada, yada.
No. I just know 3.14 and that's about it.
Well, there is a number E. Everybody say E.
Wait, isn't E like,
No, you did not say it right. You have to like E.
E? Is that better?
Wally, have y'all ever watched Wally? Don't you love Eva? Yeah. My coffee,
Wally?
I've nicknamed her Eva.
Wally.
Yeah. I love Wally.
Isn't E just like move it one way or another, a lot of zeros?
So E is, I don't know if they did this on purpose. E is an exponential function. They probably did do it on purpose. E has a value, just like pi has a value. The value goes on with no pattern, so we have no way of like recognizing, like, you know, if you round it, you've cut off value because it never ends. What is the importance of E? It comes into play with natural logarithms, which we are getting to. I hope if you didn't like natural logs, I hope to teach you in a way that you will like them because I love them. It also comes into play with compound interest problems, which is what we just bypassed for a second. I just want to look at the math behind it. I don't want to look at a word problem about it yet. So in the use for understanding E, for example, here is an example of the compound interest formula where they are basically doing like the mother function values and showing you the rate at which it's increasing. If you look at the output values over there, the dollar values. Now go to this slide right here. this slide is the graph of the compound interest formula, and then it is showing you the decimal value for E. 2.71828182884, yada 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 yada. This T-chart right here is the same T-chart that was on the other slide. The purpose of this is to show you that E is gradually approaching 2.7 in an exponential growth problem. Go to the next slide. I'm going to show you how to use E on your calculator. You have an E button. You do not have to memorize E. It is on your calculator. Let's all find it. I believe, if I'm not mistaken, it's on the left. Is it on the left?
There's a double E.
You have to hit second.
And then I.
Oh, yeah. What's that?
It's not on the left at all. It was definitely on the right. It's the division. So hit second, and then look above the division sign, and you will see the E.
Yeah, but there's one with an exponent on it.
There's one where it's e to the x power, and you can type in a number.
That lets you type in any number you want. Yeah.
400.
If you do second
70.
division sign, it will pull E to the, and then it'll give you a flashing cursor.
Okay.
I'm gonna do the same answer in a way.
It does. Yes.
Changes to capital.
All right. You're going to love these three problems right here. You are simply evaluating the value of E to these.
Hey, I know the answer to
Do
C.
you? Do you? Go to your calculator. I want you to evaluate E to the third. And please round to the nearest 10,000s. Did you say, oh wait? Round to the nearest 10,000s. How many zeros are in 10,000? 4. So check the fifth number. Alright, so let me show you how to type it in. Alright, second division sign. Caret 3. If you look at the LN button, that's why I thought it was on the left. If you look at the LN button, you will see the E to the X problem. Let me show you both. It will automatically put the cursor in the exponent's place to let you type the 3. So there are two options here, and either one of them works. I don't care which one you use. There's a reason that it's on the LN button. They are inverses. Natural log and E are inverse functions, which we are going to get into with 5.3, I believe.
Stop.
So we're going to round this to the nearest 10,000ths. That means check the fifth number. And it is definitely not enough, so this is approximately 20.
Oh yeah, approximate.
0.0855. Go ahead and evaluate B and C.
C wouldn't be approximate, would it?
Nope.
Okay.
If you want to put notes on your paper too, you can say calc. It is, you can do the second LN button. When I write LN, I always put my L in cursive because if I don't, it looks like a 1.
I couldn't find it during my ACT. I was like, where is it? I know there's a button. I don't know.
Are you going to take the ACT again?
Oh yeah.
Okay.
There's no way.
Because this is going to be very, very helpful. What is E to the 0? 1. If you need to type it, that's fine, but remember it means write the base 0 times, which means don't write it at all, which means there's an understood 1. Now, look at the two graphs for E and E to the negative X. Go to your calculator, go to Y equals, let's graph second ln E to the X, and let's graph second ln E to the negative X. Make sure you do negative, not subtract. And then now I'm going to hit zoom 6 because I just wanted a standard viewing window. Because I have no clue what I looked at last. What?
They're flipped
Yeah, they
across the
definitely-
y-axis.
Do you notice there's a symmetry about them? They what? Y'all said it.
Flipped across the
It's
y-axis.
reflected across.
Relax.
I'll be here all day. It's reflected across. I was about to say reflect. It's reflected across the y-axis. Let's take what we've learned about transformations. Go back to transformations of, it might have been quadratics and cubics and all that. When the negative is right here next to the x, remember we said anything with the x is like, hold up, wait a minute, it's counterintuitive. So I see negative x, it's actually reflecting over the y-axis. So let's make a note, reflect over y-axis. And then let's just do our best to sketch here. If you'll just sketch, doesn't have to be perfect, just to get a general idea of the two graphs. And the beautiful thing is, we are done with 5.2, but the remaining slides that I have on here are, let me help you with some My Math Lab homework problems that might be tricky. Did I include them in your notes packet?
No.
One more
This one, we're not doing.
Miss Holcombe, were you not videoing this whole time?
Another example of e
Mine
to
is
the power of
literally gone.
transformation.
Mine is gone.
Well,
I hope I'm videoing. I am. Alright. So, I got ahead of my notes.
Wait, why did you skip that?
Why is that?
that's 26.
I will do this. Let me come back here and hit insert page after, and let me just sketch. So this one was f of x equals e to the x plus 3. Okay. Just looking at these, you can sketch it. You can go to y equals on your calculator. You can type all three in. And what you can do is just remember the numbers, or the colors. Is y'all's colored? Yeah. Remember the colors that it assigns it to, and then hit graph and you can sketch it. What I want you to do is to tell me what's actually happening here. So looking at this one.
Left 3.
This is the mother function e to the x doing what?
Left 3.
It's going left 3. So if you look back at that last slide where we sketched e to the x, now just sketch it left 3. Now this one's doing two things.
Shrinking and flipped x-axis.
So we've got is it x?
No.
This is a reflection over the y-axis because the negative's up there next to the x. It also has a fraction in front of it, a decimal, less than 1. This goes back to that, hold up, wait a minute, whatever's next to the x is backwards, right? I see 0.5, that would imply shrink, so it's actually stretch. And you also need to remember the direction. It is a horizontal stretch, and the way to remember that is x runs what direction? Horizontally. So anything next to the x is a horizontal transformation of some kind. The way you figure out the kind is the counterintuitive. Like I see negative, that means reflect. Well, I'm not reflecting over the x, I'm reflecting over the y. I see 0.5. That implies shrink, but it's next to the x, so it's hold up, watch out. So it's actually stretch. So this is a horizontal stretch 5.5. Which just means now, you got to think accordion. If I'm horizontally stretching, at the same time the graph is appearing to vertically shrink. Imagine the floor and the ceiling closing. You got this nice curve in here. If I'm stretching it out and the floor is...
Ms. Holcombe,
Yes?
may I please see Aubrey Hicks in the counseling department?
She's on her way.
Thank you.
He did that on purpose to wait.
Yes, he did.
I knew you were still on there!
I didn't know he was gonna call me.
Alright, so this is a horizontal stretch by 0.5. So it's going to be stretched out. You won't see that nice elbow curve as well. It's going to be less defined. There's still a curve there though. This is another one of those, be careful. They've written it in a different order on purpose to try to trick you. There's a lot going on here. The negative in the front means what? Reflect over the x-axis. We already know the negative with the x means reflect over the y. The 2 implies a stretch. It's actually a shrink. So it's a horizontal shrink by 2. And then what's the 1 on the end? It's going to shift up 1. So there's a lot going on there. There are several homework problems that I will be taking out of the assignment because I want to hold off on them. So I think there's 14 or 16 questions total, and then I'm going in and taking some out. Let me, for the video's sake, I'm going to scroll to the next few slides so they are in the video. So if you need homework help before you get to me to ask, they'll be in the video at the end. So the first one has to do with number 4. When they ask you to graph it, a widget tool pops up. You will enter, in this case, because mine went left 4, you would enter 4 as the horizontal shift.
What time do you guys leave?
Like 5:30. Maybe fine. Can I take Timmy Ross?
Yeah, they're leaving in like 2 minutes.
And number 12. Number 12 has to do with solving it by graphing. You would type the left side in Y1 and the right side in Y2, and you look to see where they cross. Which we've done that before, but I wanted to make sure it was graphed.